Today we're just going to keep going through, we're going to finish this chapter, which is like a review of algebraic fractions. And then for the time that we have left after we're done that, I've got some exercises for us to work on. Next week we're going to start the second chapter, which is more trig. Like we kind of restricted ourselves to just working in the first quadrant last semester. Now we're going to move out to the rest, the whole plane. And so we're going to have a quiz next Thursday, which will cover material up through what we get to on Tuesday. Tuesday the 28th. So algebraic fractions and some trig. So we're going to have some exercises to work on today that's going to cover this algebraic fraction stuff. And then on Tuesday we'll have a practice quiz which will cover some of the algebraic fraction stuff, and then maybe I'll have be a little bit more heavy on the trig stuff because we won't have had as much practice on that. Before we begin adding and subtracting fractions, does anybody have any questions? Okay. If you haven't done so already, please sign the academic integrity contract. Like, if you're one of these people in the right column. And I'll just say the average time it took people to do it was 4 seconds. So, just take 4 seconds out of your life and do it.
I wonder if they read it.
What's that?
I wonder if they actually read it.
I handed it out. The statement that you read, so I handed out the document. The document's posted. The statement that you read is like one little paragraph.
Really quick.
Yeah. But that's still a valid question. I hope so. Hey, Aiden. Okay. If there aren't any questions from what we did last time, then we'll get started. So we did factoring and reducing and multiplying and dividing fractions last time. We're going to look at adding fractions, and we're just going to start with an example with numerical fractions. So the way that I kind of recommend viewing the addition of these two fractions starts with factoring the denominator. Because if the denominator is factored, as you might recall from last term, all we have to do is make sure that both denominators have the same factors, right? So we look at this first fraction, and say, well, what's in the other denominator that's not here? What's missing? Well, so that's for the second one, right? Second one's missing a 2. What's the first one missing? 5. Yeah, so give that a 5. And now both of the denominators have precisely the same factors. So 2 times 3 times 5 is 30, and then we have 25 plus 14. That's 39. And then the last thing you do, it's not always possible, but in this case it is, the last thing you do is just make sure that your fraction's reduced, and here we actually can reduce. The top factors is 3 times 13, and the bottom 3 times 10. So this is 13/10. Fun? It works really precisely the same way when they're algebraic. We just have to be careful with our algebra and our factoring and stuff. So in example 115, all these three fractions already have the same denominator. So all we're going to do is now write a single fraction with that denominator, doing the operations on the numerator. So b plus 1. And then we're subtracting 2b minus 1. We're subtracting the whole thing. So I'm putting that in parentheses. We're going to have to distribute that negative. So minus 2b plus 1. Then we just combine like terms. Simplify the top. We get negative b plus 2, or 2 minus b. So far, so good. What do we do? How do we start this next one? So, I mean, we all see that they don't already have a common denominator, right? So, Aiden, what should we do first?
So, you could multiply them all by, well, you could multiply the first one by b, and then the last one by b squared.
Okay, so so you're looking at the middle and saying that's got to be squared, so everything else needs to get up to b squared. So yeah, so we need a b and a b. The last one will need a b squared and a b squared. So that's an interesting way to approach it. I've always done it by like fraction by fraction, but you're kind of focusing on each variable one at a time. What else?
So the middle fraction and the last one both need another a. Oh no, sorry, I noticed the cube. So the middle fraction needs an a to be multiplied by a squared.
Right, to get up to the a cubed that we have here. Yep.
And then the first fraction needs to be multiplied by 1a.
Yep.
So just by a.
Yep, good. What else?
So, and then the 4 and 6 could be, so you could multiply the first one by 2.
Okay, so 4 has 2 factors of 2 and 6 only has 1.
Mm-hmm.
Good.
And then you can multiply the middle one by 2 times 2 times 3.
Yep, so that would be a 12, I think. Yep.
And the last one by 3.
Yeah, good. Okay, so that common denominator, what do we get? What goes downstairs?
12a cubed b squared.
Good. And in the numerator? Anybody feel free to chime in.
So 10BA minus 3A squared. No.
Close. What's that coefficient on a squared?
36A
Yeah.
squared. And then plus B squared.
What's the coefficient on b squared?
Plus 3.
Yeah. Good. Nice. We do a check to see if we can't reduce, but we can't. There's no common factors. I don't think there's a way to actually fully factor the top. And there's no common factor to the whole thing. Like, if I were going to be able to reduce it, based on like what I know, the factors in the bottom are pretty obvious, right? Like it's a single term. So there's not a common factor of A, there's not a common factor of B, and there's not a common like numerical factor. So I know that it won't be able to be reduced. All right. What about this one? Those denominators are different. How do we get a common denominator?
The left needs x plus 1.
Yeah, that the left needs x plus 1, because they're completely different factors. I mean, they look similar, because one's just x minus 1, one's x plus 1, but they're totally different. What does the other one need?
X minus 1.
Mm-hmm. So our common factor, x plus 1, x minus 1. Up top now we have a times x plus 1 plus a times x minus 1. The bottom I always leave factored because it doesn't really get us anything. It can actually make our work a little bit harder later on. The top, though, we need to do something. We're going to expand everything and combine like terms. So we get ax plus a plus ax minus a. What should we end up with for our result here? 2ax on top, and then this common denominator. If you want to call it x squared minus 1 on the bottom, you know, feel free to do so, but I usually just leave everything factored. Questions on that example? Okay. All right. So I'm going to just rewrite this and give myself some space. Let's see. So in example 117, the one that we just did, and the one before, there was no factoring to do initially, like the denominators are already factored. But in this one, I think we can do some factoring. So I'm actually going to start out doing the factoring we need to do. How does that first denominator factor?
Two x minus 1, 2x plus 1.
2x minus 1, 2x plus 1. Mm-hmm. And the other ones are already factored. Okay, so right now we're seeing maybe some similarities, like maybe they share some factors. 1 plus 2x is obviously the same as 2x plus 1, right? So those really legit are the same, and I'm just going to, in my next line, replace it with that. 1 minus 2x isn't quite the same as 2x minus 1, though. What can we do?
Take a negative 1.
Yeah. We'll take out a negative 1. So in my next line here, that middle fraction, instead of subtracting it, I'm going to change the sign. So I'm going to write this as plus 3x plus 1 over 2x minus 1. Like that negative 1 I took out, I'm just throwing out in front, so minus a negative is a positive. And now it's a little easier to see what we need to do. What do we need to do? What is our path forward?
We got a common denominator.
Mm-hmm.
So middle one you have to multiply by 2x plus 1.
Great.
And then the opposite of the last one.
So 2x minus 1? So now they all have the same denominator, which is, I can't draw a straight line. Let's see, 2x minus 1, 2x plus 1. So I got 4x plus this product 3x plus 1, 2x plus 1, plus 2x times 2x minus 1. Where do we go from here? Like, what's next?
You just like combine the top, or
Yeah, so like,
like multiply the 3x plus
yeah, good, good. Okay, so we're going to FOIL that out, or expand it, multiply it out. So 4x plus, okay, so this is 6x squared plus 3x plus 2x is plus 5x, and then plus 1, and then distribute the 2x, so we get 4x squared minus 2x. And now what do we get?
ten x squared plus 7x.
Mm-hmm. Yeah. And then our last step is let's check and see if it'll reduce, which means we're going to check and see if we can factor the top. So does that unfoil? I mean, if it does, we need a plus 1, I think. Yeah. So, I really, I think this example is a good one to illustrate why I resist multiplying out the bottom. There's not much that multiplying out the bottom will get us. Like, there's not much benefit to it. But when we leave it factored, we, now we're ready to see that we can actually reduce it. So we get 5x plus 1 over 2x minus 1. Ready for more? Yeah, good. All right, so complex fractions. These were fun. There's a couple different techniques you might recall. So one was that we could just work out the top by itself, do the addition, subtraction of the top, do the addition, subtraction of the bottom, and then we're looking at like just dividing two fractions, right? So complex fraction is a fraction with fractions. And if we do that here, so let's see, we'll get, let's do maybe a little side work. So the top, 1 plus 1 over, let's see, that would be x plus 1, x minus 1. And of course, the one, anything without a denominator, you make it into a fraction by putting over 1. So we need both those factors on the top and the bottom. So we've got x plus 1, x minus 1, plus 1 over x plus 1, x minus 1. We'll expand the top, x squared minus 1 plus 1. Which is just x squared over x plus 1, x minus 1. So that's the top. The bottom, 1 plus 1 over x minus 1. What do we do with this? Mm-hmm. Yeah. Bless you.
Thank you.
So we get x over x minus 1. So that's the bottom. We're dividing two fractions. What do we do?
Multiply by those.
Yeah. And now everything is already factored, so we'll just reduce, so we cancel out one factor of x, cancel out the x minus 1, and we get x over x plus 1. We have another way to do a problem like this. The other technique involves, factoring everything, keeping everything written as that complex fraction, but just factoring denominators. Over 1 plus 1 over x minus 1. And then saying, okay, I've got this big fraction. I'm allowed to multiply the top and bottom of a fraction by the same thing. So what I'm going to do is look at all the little fractions that appear. I've got two little fractions that appear. And the LCD of those two, like just grab all the factors I need, which would just be an x plus 1, x minus 1. That takes care of everything. And then multiply the top and the bottom by that LCD. And that's the same as just multiplying each term by that LCD, because what we're going to do is now distribute through the parentheses, each of these. So when we distribute that, if we just focus on the top first, if we distribute that factor to the top, I'm just going to get x plus 1 times x minus 1, because I'm multiplying it by 1. When we distribute it to the second fraction, these are going to cancel, and we just get 1. So we have x plus 1, x minus 1, x plus 1 times x minus 1 plus 1 over. When we distribute it on the bottom, what do we get? For the second term, yep. And then for the first term, it's still just multiplied by 1. So yeah, x plus 1 times x minus 1. And then plus, the x minus 1's cancel, so x plus 1. And then we just expand both of those out and reduce if possible. So we have x squared minus 1 plus 1 over x squared minus 1 plus x plus 1. And then we see what we could do factoring wise. So we have x squared on top over the plus 1 minus 1 cancels. X squared plus x means we could factor out an x times x plus 1. And we can cancel an x. And we get x over x plus 1. These two different techniques are equivalent to each other. They'll always lead to the same result, and so the technique you choose really is just a matter of preference. Let's do another one. So complex fractions are fractions within fractions. And, you know, at first it looks like this is not a complex fraction, but of course it is, because somebody's trying to hide fractions in fractions by using negative exponents. I see through that every time, right? So they can't fool us. We know that they're just trying to hide fractions within fractions and hope that they don't have to simplify. We know better. So first let's write it as a complex fraction that we know it is. So we've got 1 over x plus, what's that second term as a fraction? 2 over y squared. Good, right. So that negative exponent is only on the y, not the 2. The 2 is in the numerator there. And then on the bottom, 1 over x minus 2 over y squared. This one is actually really simply done by using that second technique. I think is a little bit less work. So the LCD is pretty clearly identified as xy squared. So we'll multiply top and bottom by xy squared. Sometimes it can be helpful to actually do the distribution, like write out the distribution explicitly. So we would have 1 over x, 2 over y squared. This would be times xy squared. On the bottom, 1 over x minus 2 over y squared. And then just start canceling. So the x cancels, the y squared cancels, and in the top here we've got y squared plus 2x. In the bottom the x cancels and the y squared cancels, and so we have y squared minus 2x. And I think there's no common factors there. They're both unfactorable, so that's just where we're at. Okay. Want to solve some equations? Overwhelming support there. So, you know, again, we did this toward the end of the semester last term. So, our approach is just identify what the LCD is, multiply through everything by the LCD. We don't need to attain a common denominator. So, like, we don't have to do the addition subtraction. You can. It's just that that's more work. It's easier to just say, here's my LCD. I'm going to multiply every term by the LCD and then like cancel everything that cancels. If you've done that step right, you'll have an equation with no fractions. And then you just solve that equation that you see. So what's the LCD here? These are just numeric denominators. So
Just 2.
not the greatest common factor, but the least common multiple.
24.
24, right? The smallest number that they all go into. Now, when you have numeric denominators, any common factor or any common multiple will do. When you have algebraic denominators, still you could use any common multiple, but that has a way of making the resulting equation substantially more difficult to solve if you don't use the least common denominator. So we'll multiply everything by 24. Which means every term gets zapped. And then 12 goes into 24 twice, 8 goes into 24 3 times, 6 goes into 24 4 times. And now we've got 2x minus 3 equals 4 times x plus 2. move over here. It's a nice linear equation, so let's go ahead and solve it. I'll distribute that 4. And then get all of my x's on one side. Add 3. And by the time you finish that step of clearing your denominators, usually we're looking at an equation that's not too hard to solve. A lot of the time they're linear equations. Sometimes they might be a quadratic, but we can just reach back to what we know about solving quadratic equations then. We have a negative 2x equals 11. So dividing by negative 2 gives us negative 11 halves. Want to do another one? Do you have a question, Stefan? Oh, okay. You're way back there, so it's kind of weird. Oh, you're charging. Yeah, okay. Okay, what's the LCD here? What factors do we need to make sure we get them all?
N plus 2 and 2.
N plus 2 and 2 and n. Yeah, yep. We just grab them all. They're both factored already and nothing in common. So we'll multiply both sides by that LCD. Do some canceling. The equation that we get, 2n times 5 is 10n equals 3 times n plus 2. So 10n is 3n plus 6. And it's a nice, linear equation. I'm not going to belabor the process here. This is old hat to us. 7n is equal to 6. And so that means n is 6/7. Sometimes people see an equation like the one that was given to us, right, this one right here, and they'll say, well, I could just set the cross products equal to each other. And you can. That's a legit move, but only if each side is just a single fraction with nothing else being added and subtracted. So if you did set the cross products equal to each other, you'd have 5 times 2n, 10n, equal to 3 times n plus 2, which is exactly what we got here. That trick only works if each side is just a single fraction and nothing else. So, and that's fine to use if you're in that situation. Just don't purposefully avoid using the technique of the LCD, because that works for all equations that have fractions. What is the LCD for this equation? Yeah, good. So I'm going to just write it again, leaving some space for myself. So I can write in this factor, or this that we're going to multiply by. So 3x, 3x, 3x. Cancel what will cancel. What's the equation that we get?
3x minus 3.
Mm-hmm. Good.
3 plus 2x.
Good. Nice linear equation. Let's solve it. 3x minus 9 is 3 plus 2x. We get our x's on one side. Get the constants on the other side. So we get what, x equals 12. When you're solving an equation with fractions, and I've kind of glossed over this this time, but you want to just make sure in the end that it's an allowable value for x in the equation. What do I mean by that? Yeah, like if I put it back in, I want to make sure it doesn't make any of the denominators 0, and obviously 12 doesn't, right? The only problem value of x here would be x equals 0, and the last one, problem values of n would be 0 and -2, and that was just numerical. So a lot of times, like when I finish, like when I just get started and I make sure I can see I know what my LCD is. Usually it's at that point that I say, okay, like just take a mental note of like what my variable is not allowed to be, and then just check my answer against those. No factoring to do here. What's my LCD?
X times X plus 2.
Good. So everything will get zapped by the LCD. Cancel what will cancel. What equation do we get?
Not sure they handled the first one, but 2x.
Yeah, that's exactly how you handle it. It's all over 1, like it's not a fraction. So nothing cancels, not a fraction.
I wasn't sure if that went to both the parentheses and because when we cancel, they're separate terms. But
well, I mean, when we multiply, we just have these factors. We'll distribute, in the next step. But what about the next one?
minus x plus 2.
In parentheses, right? Like, as we're subtracting the whole thing. And what do we get on the other side?
3x.
Great. Now let's multiply, let's expand. So we have a 2x squared plus 4x minus x minus 2 equals 3x. What kind of equation is this?
Linear.
Say that again.
Is it linear?
What makes it linear? What makes an equation linear, actually? That's a good question. I've been throwing that word out a lot, but like, how do I tell algebraically, just by looking at what shows up, whether or not an equation is linear?
The other side of the equal sign doesn't have the power of anything greater than.
It doesn't have anything to do with what's on one side versus the other. Different terms? Yeah, so to be linear, you can only have x to the first power. Just a number times x. This has an x squared. So what kind of equation is it?
Trinomial.
It is a trinomial. The type of equation, well, once we simplify, it'll be a trinomial. We can write it in 3 terms, but it's quadratic. Yeah, it's a quadratic equation. So, let's get it set equal to 0. Let's subtract 3x from both sides. We get 2x squared plus, oh no. Yeah, minus 2, right? There's no x's. How do I solve a quadratic?
Quadratic form.
Okay. Look, that will get the job done, okay? But if we want to, like, have a good time with it, okay?
You complete the square.
We could complete the square. We could also factor it. Quadratic formula, like, I'll never ask you to use a quadratic formula. If there are no instructions, use a quadratic formula. If you really like it, use it. But
First thing in the instructions on the test is no quadratic.
yeah. So we could factor or we could complete the square. Let's factor first, then we'll complete the square. We'll do them both. Might as well. So we could take out a 2, and then we get x squared minus 1. Can we factor that? How does it factor? Yeah. And here's, the trick with factoring, what makes it work is that it's a product set equal to 0, right? Because that way we could say if I multiply two things to get 0, one of them has to be 0. 2 is never 0. So we just have to focus on those other factors. This means that either x plus 1 is 0 or x minus 1 is 0. And that gives us the results x equals -1, x equals 1. Those are our two solutions. Those are the solutions you'll find if you use the quadratic formula. And if we complete the square, there's not going to be a whole lot of completing the square to do because there's no x term. But when you complete the square, the first thing you do is throw the constant on the other side. There's no x term. There's no square to complete. So, or it's already perfect square. Like if we divide by 2, we get x squared equals 1. And that means that x is plus or minus 1. How's that? Pretty nice? Okay. All right. So we have like a half hour left. So I've got a handout with some exercises dealing with factoring and algebraic fractions. I'd like you to spend some time working on that today, for in the rest of our class time, and then when you're done, feel free to go. My solutions are posted on Canvas right now. If you go to today's the page for